Okay, good afternoon, everyone. So today it is my pleasure to introduce our ECR speaker, Alexandra Dupuy from CIAS. Alexandra Dupuy from CIAS. That's the one thing I should have checked. Alexandra did her PhD in Lyon, supervised by Hélène Courtois, and was a postdoc there also before coming to CIAS in 2022. And today she'll be talking to us about measuring the local universe with Cosmicflows-4. Please, Alexandra, start when you're ready.
Okay, so thank you for letting me give a talk today. Okay, so let me start. So we all know, I guess, here that the large-scale structure that we see today in observations, such as this map of the universe given by SDSS, are caused by the tug of war, actually, between the competition between the gravitation and the expansion of the universe. And actually, gravitation can be seen through the peculiar velocities of galaxies, which are actually the part of the total velocity of galaxy caused just by gravitation. And they allow us then to probe the total matter in the universe, so both the dark matter and the baryonic matter. And then in the linear regime, we have this relation between the peculiar velocity field and the overdensity field. And observation give us only the radial part of peculiar velocities. Actually, we don't have the full three-dimensional part, unfortunately. And this is the most simple relation to get the peculiar velocity, radial part of peculiar velocity is this one, Cz minus A0d, where d is actually the distance of galaxies. And we have these catalogs prepared by the Cosmicflows collaboration that are listing the distances of galaxies and also group of galaxies. So there are many Cosmicflows catalogs. So it started with Cosmicflows-1 in 2008 with just a bit less than 2,000 galaxies, and then Cosmicflows-2, Cosmicflows-3, and finally Cosmicflows-4 with over 50,000 galaxies. So these, it's actually not galaxies, but distances of galaxies. So these distances come from many different methodologies, actually. It's just a compilation of many methodologies. And mainly, I would say the Tully-Fisher relation and the fundamental plane, but also other methodologies such as SBF, supernovae, and Cepheids and masers. And they also, all of those observations, measurements that we need to get in the end, the distances come from many different telescopes. So we need both radio telescopes, for example, for the Tully-Fisher. We also need optical telescope that may be in Hawaii, for example, or in space. So it's many different methodologies, many telescopes. It's very, very various. And before moving on to what I want to talk about today, I just wanted to show you, for example, this measurement. So you have, for many different galaxies, both of the radio measurement that we did for Cosmicflows-4 actually. So this is the H1 spectra. And also for the same galaxy, which also show the optical image. And with these two different measurements, we apply the Tully-Fisher relation to get in the end the distance. But I won't talk about this today. Okay, so now what I'm going to talk about is mainly the Cosmicflows-4 catalog. And it is shown in this plot, which is actually a three-dimensional plot in supergalactic Cartesian coordinates. So you have the x-axis, the y-axis, and then the z-axis. And each dot corresponds to a galaxy of Cosmicflows-4, and the color corresponds to the distance the redshift in kilometers per second. And at the back there, you have a night of plot, also in supergalactic coordinates. So you have SGL, SGB, and you can see also here there is no galaxy because it's the zone of avoidance because of our galaxy. And yeah, and you can see on both of the 3D plot and the height of plot that Cosmicflows-4 is actually very asymmetric. There are many less galaxies in what we call the south hemisphere than in the north hemisphere, because you have here this all this part which is coming from the SDSS data actually that has been added to Cosmicflows-4, and which correspond to this red part that you see in the height of plot. So from the distance of the distances of galaxy in the Cosmicflows-4 catalog, you can get the peculiar velocity, the radial part of the peculiar velocity, which you can actually see in this slice on the left plot. So this is an XY slice in supergalactic coordinates centered on the Milky Way. So we are at the center, and each dot corresponds to a galaxy of Cosmicflows-4. And I added the radial part of the peculiar velocity, represented by these little red and blue arrows. So the arrows are blue if the galaxy is coming towards us, so for a negative peculiar velocity, and red if the galaxy is going away from us, so with a positive peculiar velocity. And you can recognize actually the different structures, the different superclusters that we see, which are actually at the same place, where we see a lot of red and blue arrows that are crossing. That's how you recognize supercluster. So you have the Hyper supercluster, the Perseus-Pisces supercluster here, the Coma supercluster, Shapley, and also in the SDSS part, the Sloan Great Wall, for example. So from this, we can actually go from the radial peculiar velocity to reconstructing the three-dimensional overdensity and also three-dimensional peculiar velocity fields. So I won't talk about this methodology. This is done by actually my PhD supervisor, Hélène Courtois, in Lyon. So she's using what she calls the Hamiltonian Monte Carlo algorithm to reconstruct from the radial peculiar velocity of Cosmicflows-4 the 3D overdensity and velocity field. And this is what she gets after applying this algorithm to these peculiar velocities. So this is, the right plot is the same XY slice, supergalactic coordinates, and the color map is the overdensity field. So you have underdensities in blue and overdensities in red. And the arrows correspond to the three-dimensional peculiar velocity field that has been reconstructed. And you can once again notice that the non-structures, non-supercluster, have been reconstructed. So what I want to talk about today is what you can do with such three-dimensional reconstructions. So supercluster, as per the definition given by the Cosmic Web, can be defined as a set of knots, filament sheets, and voids. And actually, we can give another definition to supercluster, a more dynamical definition based on peculiar velocities. So we can define a supercluster as a watershed, or also we can call it a gravitational basin that can be either a basin of repulsion in the case of supercluster, but we also can define basin of repulsion, attraction and basin of repulsion. So this is just what I want to define before going to the next slide. So this is just a random velocity field with two attractors, what we call attractors, which are actually two attractors and one repeller, which are actually the critical points of the velocity field. And I also want to define what a watershed is. Actually, it's in the case of lakes or rivers, it's actually the area that drains all the water into a lake through a different stream or through different rivers. So we'll do the same, but with galaxies and velocities. So we'll define watershed at all the area where the galaxies go towards the same point, actually. So for this, we are going to use streamlines. So from the velocity field, we can actually derive the streamline by just integrating the velocity field from different seed points. So from the voxels of the velocity field. And then we can actually define the basin of attraction in this case as the set of all of the streamlines, all of the streamline points whose streamline converge toward the same attractor, toward the same critical point of the velocity field. So we have here 2 attractors and 2 watersheds, 2 basins of attraction. And this is the case if you integrate the velocity field in what we say the forward direction. So we just integrate V. But you can also integrate the velocity field in what we call the backward direction. So integrate minus V. So if you integrate minus V, instead of detecting basins of attraction, you actually detect repellers and basins of repulsion. And in the literature, there are actually just 3 structures until now that have been defined with as watersheds, as basins of attraction or basins of repulsion. So the most famous one, I would say, is the Laniakea supercluster, which is our home supercluster, the supercluster we are part of, the Milky Way is part of. And also we have identified, the authors have identified the dipole repeller and the cold spot repeller. And actually now with Cosmicflows-4, we have many more, not new basins because it's structures that we know already, but newly defined structures as watersheds. So this is the updating map of watersheds. So we still have the Laniakea supercluster. So this supercluster is the one in red here. But now we define all of the structures around this, around the Laniakea superclusters as watersheds as well for the first time. So for example, the Perseus Pisces watershed, the supercluster that you see here, is now also defined as a basin of attraction here. Same for Chapelet, Hercules, Lepus, and also all of these new structures that have not really been given names yet, but one of them is probably the Sloan Great Wall, have also been defined as attractors with a respective basin of attraction. And this is a very similar plot, but maybe a little bit less fancy. So you see once again the same structures, the same superclusters with the streamlines to show the different basins of attraction, and the little spheres here are located at the coordinates of the attractors that have been detected. So yeah, and so on the left plot, you see, once again, to show basins of attraction before moving on, you see an XY slice in supergalactic coordinates, always centered on the Milky Way on z equals 0. And the color map is the overdensity field, so it's the color map that I showed a few slides before. And I added to this slide you see like these different regions, these different areas, and these are actually the different basins of attraction that have been detected. So you have here the Laniakea, which is actually this one, and oops, what's going on? Sorry. Okay. And also the Perseus-Pisces supercluster, the A+ supercluster, Shapley, and I didn't show them because it would have been too crowded, but you have also all the SDSS basins of attraction that should be up there. And you may remember what I say, that you can define basins of attraction, but also if you integrate the velocity field in the other direction, you can define basins of repulsion. And this is, I am showing them in this three-dimensional plot, and also as these little lines here. So the solid line here corresponds to the sculptor void, and this one here corresponds to the Bootes void. So, and they are also showed like in the three-dimensional plots here. So for the Bootes void repeller, that's how we call them here, and the repeller corresponding to the sculptor void here. And you may remember I mentioned the dipole repeller and the cold spot repeller. We actually identify it as a single entity in this case, so as a single repeller, which is actually located just between the two locations that have been published in the literature, which are corresponding to these two cospheres. And before moving on to the second part of my talk, I want to show you a cool thing that we can do with streamlines actually. So instead of just following the streamlines and identifying the point where they converge and then just identifying, detecting watersheds, basins of attraction or repulsion, you can actually just make an histogram, a density of the streamline. So you take the velocity field, you construct the streamline, and you just count how many streamlines go through each cell. And with this, you can actually make some kind of skeleton of the velocity field. And this is what is shown here. So the left plot is an XY slice of this, what I call density of streamline. There is no real name yet for this measure. And so in black, you have a low density of streamline, and then in purple, in orange, you have a high density of streamline. And you can actually notice the different watersheds, the different basins of attraction that I mentioned before. And you can see how they are all connected kind of to each other. So you get some kind of a skeleton of the CF4 velocity field. And on the right plot, this is actually a plot that I prepared, that I made, I don't know, maybe 2 years, 3 years ago. It's the same, it's the density of streamlines computed on a constraint simulation of the CF2, Cosmicflows-4 data. So it was much smaller. That's why the cube is not going as far as the CF4 one. And so since this is a constraint simulation, so it's a lambda CDM simulation constrained with the CF2 data. So we are supposed to have the same structures, the same supercluster that we see in the CF2. So that's why we can notice the Laniakea supercluster, the Perseus-Pisces structure, Coma, and also Shapley here. And you can see that there, if you just visually compare, they are somehow similar, located at the same place, and with much less details, of course, in the data. And if you compare actually the size, I have not shown the volumes or anything in this slide, but they are also very similar in size from the lambda CGM simulation to the data. Okay, so I have not said anything about the reconstruction methodology that has been used to get those peculiar velocity fields. But I want to mention the limitation of of this method. So on the Cosmicflows-4 catalog, so with around a bit more than 50,000 galaxies, it actually took around 2 to 3 weeks to compute the overdensity and peculiar velocity field. And the question is, we are expecting many large-scale cosmological surveys, such as Wallaby, TESI, and also Foremost, that are going to bring many more galaxies. So the question is, can we still use, for example, this reconstruction methodology that is used in the Cosmicflows-4 collaboration, or do we need a new one? And this can actually be answered with the deep learning. And that's what I'm going to present now. So before moving on, before explaining the actual architecture, I just want to show you this map very quickly. So this is, on the left plot, you have a slice, XY slice in supragalactic coordinates of the predicted dark matter map predicted from a deep learning model with the Cosmicflows-4 peculiar velocities. So in blue, you have always the underdensities, the region with no galaxies, and in red, the clusters, the region of overdensity. And yeah, you see that it's working quite well. The model has managed to predict overdensity near actual structures, known structures, such as Virgo, Ursa Major, Fornax, Eridanus. And on the right side, it's actually the same map, but this time shown on a night of map in galactic coordinates. So you have here the L and B. So you have here the zone of avoidance, the region that is hidden by the galaxy. And in white, you have the color map is from white to black. So white underdensities and black overdensities. And what you can see is that once again, the model has predicted overdensities around the same area as the actual known the galaxies are. So you reconstruct, you predict the different clusters that we know. And also, as you can see, I added those little blue dots, which actually correspond to galaxy coming from H1 surveys. So within the zone of avoidance. And you can see that the model actually managed to predict overdensity in this area where we actually are not supposed to have galaxies because it's hidden by our own galaxy. So despite having no data in there, it still predicts actual overdensities that seem to actually correspond to clusters, because we can see here, for example, there are few galaxies here. This one, there are a few galaxies as well. We see on the other regions a little much further. This little overdensity is overlapping with galaxies also here. And here it's a little bit more messy, but it still seems to correspond to actually the puppies, for example, cluster. So since we know that this deep learning algorithm that we use for this map, that I will just introduce after this slide, may help us identify clusters, structures within the zone of avoidance, so behind our galaxy. We are thinking, can we use it actually? So can we make first a bigger map and also then use it to actually detect and confirm the position of the grid attractor? So yeah. So this is the architecture, deep learning architecture that we use. So we use a convolutional neural network or unit type to reconstruct the dark matter density field from two types of observational data, so the galaxy position and the radial peculiar velocities. So this is the actual architecture, so with an encoding part, a decoding part, and concatenation to connect the two parts. And the first thing I want to show is the training on the illustrious TNG simulation. So the size of the box, of the entire simulation box, is 205 megaparsec H. And the final grid size that we want for the output for the predicted dark matter density will be 160 megaparsec H. And you may, before moving on to the training and then the results, you may ask me, why do we need the radial peculiar velocity in the input, not just the galaxy position? So I want to show you this plot, which is showing slices on the YZ plane. So from left to right, you have the galaxy positions, then the radial peculiar velocities, then the true value, so the value that we give to in output to the model, the true value of the dark matter density, and this one, the fourth plot, is the predicted overdensity using these three the both inputs and the output. And the last panel is actually the same slice, but with only considering the galaxy position, so without considering any peculiar velocity. And you can see, so by comparing these two here, you can see that there is something lacking. We are lacking some, it's like we are lacking all the cosmic wave part of the dark matter map. So we don't really see any link between the different structures that we are supposed to see, for example, in the true value of the dark matter map. So that's why we need actually to include the peculiar velocity field, the peculiar velocities in the training. So for the training, we use the TNG 300 simulation. So we use both the galaxy catalog that you see on the left and a CIC computed from the Halo catalog of the TNG. And so since we need to have to make some kind of mocks that look like the observation, we first need to identify Milky Way-like galaxies that will be the centers of all the training samples that we'll make. And then we recenter the simulation, the Halo catalog, and the CIC on each of those Milky Way-like galaxies that we identified, and we make this 160 cube around each Milky Way-like galaxy. So this cube that we made from the CIC will be the output. So it will be the output channel. And then we still need to work a bit more for the input channel. So we really need to mimic observations. So we need to construct more catalogs that have the same spatial distribution of the Cosmicflows as the Cosmicflows-4 catalogs. For example, we need to mimic the zone of avoidance. So we actually shouldn't have any galaxies within the zone of avoidance. So we need to try to make mocks that reconstruct this characteristic of the Cosmicflows catalog. So what we do is that we try to mimic to have all those mocks have the same probability density function of L, B, and the redshift CZ as the Cosmicflows-4 catalog. So for this, we cut, it was just much simpler, it was working better. We cut these samples into two parts. So a closer part, the low redshift part, before 3,500 kilometers per second, and then a high redshift part after this threshold. So for the low redshift part, we only removed the zone of avoidance, so with a B cut, and we fit the PDF of the redshift only. And then for the high redshift part, we fit all three PDF, so LB and CZ. And to fit those PDF, we use a Monte Carlo algorithm, which I won't really introduce here, but it's coming from this paper. And this is what we get. So we have here the same, the XY slice of the CF4 catalog, actual CF4 catalog. And this little circle corresponds here to this cut that we are doing. This is an example of one of the TNG 300 mock that we made with this algorithm. And these are the PDF that we actually try to fit. So you have in purple the CF4 PDF and in green the TNG mock PDF. And you can see that the algorithm that I used to make them fit actually worked perfectly, almost perfectly, because the two PDF are overlapping. And yeah, you may see that there is a little difference for the PDF of the redshift. So we use the VGSR, Galaxy Standard Forest, in this case. Because of the resolution of the simulation, there is not enough galaxies at low redshift to exactly fit with the distribution of the CF4 galaxies. And on the bottom part, you can see two height of slices in galactic coordinates of, at the left in purple, the CF4 data, and on the right in green, the mock from the TNG simulation. So you can see here mainly that we managed to reconstruct the area where we should have very few galaxies, very few measurements, because it's the zone of avoidance. So we have now these mock catalogs, and we need to prepare the input channels. So for the first input channel, which actually represents the galaxy position, we just make some kind of very simple CIC. So we just count how many galaxies are in each cell of the box. And then for the second input, so the peculiar velocity, we actually have the three-dimensional velocity from the simulation. So we need to extract the radial peculiar velocity because that's what observations give us. And that's what we do. We extract the radial part from the 3D peculiar velocity. And then we just make some kind of CIC once again. So in each cell, we just put a value that corresponds to the average peculiar velocity, radial peculiar velocity. So we have these two input channels now. We also have the output channel, so we can now run the training. So the left plot shows the loss as a function of the learning rate. So the loss is just the MSE, that we defined it as the MSE. And yes, so this part is just to choose the best learning rate value that we can use. So we actually choose values between in this blue area because it's going down slowly, so it will be the best value that could train the model. And then the right plot is showing the MSE as a function of the epoch. So this is the actual training. And we used 10,000 samples for the training set and a bit more than 1,000 samples for the validation set. The model has been trained over 400 epochs. And the blue line is the training loss, and the orange line is the validation loss. And in the end, this is what we get. So these are two XY slices. On the left, you have the true value of the density field. This is just one random validation sample. So you have the true value of the density field, so what we should get, what we have given, what we should give in input to the model. And then on the right plot, you have the same slice, but predicted by the deep learning model. And you can see that it's actually doing very well. So we're a construct, we can notice, recognize structures that are actually also easily identifiable in the true value of the density field. So for example, this structure here, this structure here, and also the voids, actually the actual voids here. We are not supposed to have any galaxy, and we don't have any. And what you may tell me, and that's actually a comment that I got at a talk I gave 2 months ago, is that the size of the simulation is actually way too small compared to the size of the cube that we are trying to predict. So you can see it here, it's just almost the same size actually. So we may have maybe too much overlap between the training and the validation samples, and it may cause some issues with the training and the prediction. So we decided to move to the ASIM simulation, which is much bigger. So we moved from 205 megaparsec H to 1200 megaparsec H. And I won't explain all the way back the method. We use the same method. So we just take the Halo catalog of the ASIM simulation, we get the CIC, aside we get the Galaxy catalog of the ASIM simulation to prepare the inputs the same way as we did for the TNG. And here, so yeah, so we get the MOX, we prepare the input channels, so the galaxy position, the radiopecular velocities, and then the output channel, the true value of the density field. And the training is actually, it's done similarly as the TNG training for now. So we have 10,000 training samples, 1,000 validation samples. We run the training for 400 epochs, and we choose a value of the learning rate that is chosen from by looking at the loss function as a function of the learning rate. And that's what we get. So this is just the same same slices that I've shown before, but now for the ASIM simulation training. So on the right part, you have an XY slice of the true value, the ASIM CIC of the density field. And then on the right panel, you have the same slice, but this is the one predicted. This is the density field predicted by the deep learning model. I can make the same comments once again. We can notice the same structures and similar structures, the same cosmic web as between the prediction and the true value of the density field. So this structure that should connect somehow to this one, and then all the way there, this structure here, this structure, a big void, for example. So it seems to be working well, but the main goal is to check it on actual data, not on simulation. So we can apply it to the Cosmicflows-4 data. And just to compare, I am showing both training, so the TNG 300 training and the ASIM simulations training. So these are the same sizes as usual, which is the easiest one for the cosmography. So XY slice in supergalactic coordinates centered on the Milky Way. And in both predictions, you can recognize the known structures. The little dots are the actual CF4 galaxies. So you recognize the Virgo, Hydra, the Sharpless cluster, the Coma, Perseus Pisces, Southern Wall, the Sculptor Voids, and same in this case, we recognize the same structures. And by comparing these two maps, you can see that the ASIM prediction seems a bit more detailed than the TNG 300 one. So it's maybe can be explained by the fact that the ASIM now is the ASIM simulation is much bigger, so we have less overlap between the training samples, so it allows the model to learn better. And just to, I guess this is almost my last slide. So these are the height of density maps for the ASIM simulation only at different ranges, 1020, then 2030 megaparsec H, then 3040 and 4050. I didn't decide to go further. And so the color map is the density map from white to black, so under density to over density. The yellow to red points are the CF4 galaxies, and then just like the plot I showed previously, the blue points are the galaxies from H1 survey, so within the zone of avoidance, because this is what we're interested in. So we can see that the model has once again reconstructed the overdensities at the location of actual structures. So I've not added any names because I made this plot yesterday. So I'm not sure what each structure is, but yeah, I mean, we see a filament here, which is overlap with the CF4 galaxies, and yeah, it's nicely overlapping for each radius. And same, it's a bit messy for the zone of abundant galaxy, but we still see, for example, here we do have a cluster and we have a predicted overdensity. Same here, and it's it's a bit faint, but we do see also a predicted overdensity here. And actually, I need to check a little bit more this, but this location is supposed to correspond to the direction of the great attractor. So the question is the overdensity that we predict here, the overdensity corresponding to the great attractor. So to confirm this, I guess we need to use the velocity field to see if we actually have some kind of convergence towards this area. And this is the plan for this is the next plan actually. And yeah, I leave you with my summary. Thank you.
Thank you very much for that very nice talk. So does anybody have any questions for Alexandra? Please raise your hand. So I think Miguel was first. You want to go ahead?
Yes, hi. Thanks a lot for the talk. It was very, very interesting. I have a lot of questions, but I'll probably just keep it to one or two to not bore you. So the first one is probably a bit basic. So I was looking at, so I'm very, like, I know nothing about reconstruction and all of this, but when you were introducing Cosmicflow, you introduced a bunch of several methods to compute the distance. That are, none of them are redshift, right? It's just like different tracers or whatnot. Do you know a little bit of how do you get like the final distance measurement from all of this? You mentioned Tully Fisher, fundamental plane, supernova, all of that.
So I'm mainly involved in the Tully-Fisher method. So
Okay.
for the Cosmicflows-4, I got the radio measurement actually from this telescope, the Green Bank telescope. And I am the one who got these spectra, which are actually the H1 line spectra, so that we get to, in order to get the line width, which is connected to the rotation velocity of the galaxy. And then with the Tully-Fisher relation, we connect the rotation velocity to the actual oh, I forgot. I forgot how to say it in English. I'm sorry. Anyways, I mean, you get all those parameters to, in the end, fit the distances. So what I know, I mean, I'm only involved in the radio part, so I cannot really answer to those questions about then the actual method that we use to compute the distance. But I know that they actually, I don't really know.
No, it's fine. It's fine. I was just wondering if the distances that you have are like a summary statistic or whatever, but it's not important. So also, for what I understood, you are connecting these distances to redshifts, right? In order to get the velocity, line of sight velocity. Do all of the redshifts come from the CERN survey? And if not, is it like issues with like systematics of redshifts coming from different places or something like that?
I guess they do come from different places as well.
Mm.
I mean, now they have, but the redshift is quite, I mean, the uncertainty on the redshift is very, very, very low. So I don't think there is much issue with this, but the issue with the Cosmicflows-4 catalog is that the distance of galaxies, whose uncertainty is big, it's very big. And it's already an issue. And on top of that, it's coming from different methodology, different places, different telescopes. And this is the biggest issue actually with the Cosmicflows-4, but we can't really do anything about this because it's one of the only few catalogs that are listing this, giving this kind of data.
Makes sense. So I have other questions, but I'll let other people go ahead.
Other questions? Benedict.
Hi, thanks for the great talk. I have a question about how you select your Milky Way-like galaxies in your mock catalog. So is it just on based on mass only, or do you have other criteria? Like, do you consider whether the environment kind of looks like our Milky Way as well? That the distribution of
no, for now it's just a mascot.
Okay,
it's simply a mascot to have the mass similar to the Milky Way. Yeah.
so it's not really important whether you have attractors kind of and repellers distributed similarly to our Milky Way around your mock.
And I don't know about that, but I mean, to select the centers, I just do a mascot, but then for all the distribution thing, I'm just making sure the PDFs are looking exactly like the Cosmicflows-4. So maybe that helps having the same kind of environment. I don't know. But yeah, I mean, for the cut itself, it's just a mascot.
Great, thanks.
So I have a quick question about the velocities. So with the radial peculiar velocities, you're actually computing the velocities there? You're not working with something like log distance ratio?
No.
Okay.
So go from radial peculiar velocity to just the three-dimensional one.
Yeah. But no, I mean, so when you measure the distances, you really are using velocity. You're going from distance to cosmological redshift and then subtracting it from measured observed redshift to have velocity. Do you correct Are they in the frame of the galaxy then? You don't shift into the CMB frame. What frame are these velocities in? Is my question.
So in the deep learning methodology, it's in the galactic standard frame, so GSR, while in the other one, in this one, it's in the CMB frame.
Okay. Yeah. Okay, that's what I was asking. So in the reconstruction, the Milky Way, if you like, is motionless.
Yes.
Whereas here you have to, yeah, got it. Okay, great. Other questions? Miguel is probably waiting to ask, but let's see if anybody else raises their hand. Okay, do you want to go again?
Yeah, sure. Thank you. So I have probably a bit of a technical question, but I noticed that when you were showing your MCMCs, you were sort of fixing the learning rate at a value where you showed that it like performed the best, right?
Yes.
But so when I've in other works that I've done, we actually found that it's like very convenient to actually change the learning rate at given steps when you're training.
So actually, the learning rate is not fixed.
Okay.
So for example, in this case, the learning rate, we use a triangular cyclic learning rate. So it's not just a fixed value, it's varying between these two values that we set. So it's varying between this value and this value at each epoch, actually.
And so cyclic means that you are trying all of them? Like every epoch you try all of them and then move to another epoch and try again or something like that? Or... Oh, wow.
I mean, it tries different values. Yeah.
Okay.
Kushal, you have your hand raised.
Yeah, so I just wanted to ask, so I see that your loss function is MSE, so I presume like for the entire box, you calculate the MSE, right? So are you trying to check whether it's biased or not? So maybe that mean is predicted accurately, but overdensities are much more overdense than the truth, and underdensities are maybe less or...
Yeah, I have not worked on any errors or uncertainties for now, but yeah, definitely it's something we should do.
Okay, thank you.
And we also need to, I guess, I mean, on top of this, we also need to include the uncertainty on the distance. I mean, on the perpendicular velocity. So we have the uncertainty on the distance that is like propagated to the radial perpendicular velocity. So we need to include this as well.
So if I understand correctly, you are passing uncertainties to deep learning model somehow?
I mean, the most easy option, the easiest option would be just to run the deep learning model on different values of perpendicular velocity within the uncertainty. So this is just the easiest options.
But I don't think deep learning models are supposed to are built to have uncertainties in their input samples.
No, it won't have uncertainty, but we would just have so we would just run the model many times. So on, I don't know, 1000 realization with different values of the perpendicular velocity within the uncertainty. So with between plus and minus delta, whatever we have, delta V. And from this 1000 realization, we would get 1000 prediction. And from this, so 1000 maps, and from this we can get the mean field instead of just having the phase value of the perpendicular velocity, and also the standard deviation of all those realizations. So that's what I mean by just trying to include the uncertainty, observational uncertainty actually. So this is, in any case, it's not included in the model itself.
Okay, thank you.
So how fast can you train a neural network then, if you can run thousands of them?
So the model is trained, the network is actually trained just once. So it's trained just once on the simulation, so TNG or ASIM, on those 10,000 samples. And then, so this takes, I don't know, 5 days, I would say. And then that's the cool thing about CNNs is that after we can apply it to the data as much as we want. We don't need to train it again to apply it to 1000 realization. So after this 5-day training, we get one model that we apply to the phase value of CF4 peculiar velocities, or those 1000 realization that I was talking about. And this takes just a few seconds.
Okay.
I have a quick follow-up from Kushal's point. So I think Kushal was making the point that if with MSE, you're basically treating every point as having the same weight. Whereas some work that I did recently with Faye, who's now at Kias, of course, but was here, and some work from Chris Sabiu, we did a reconstruction where we weighted different pixels with different weights based on like density and velocity. So to try and recover better the high density and the low density regions.
Yeah, one thing that we considered at some point was using a loss function to focus on over densities only, because that's what is interesting for us. So yeah, maybe change the loss function, use another loss function to focus on the over density.
Yeah, you could apply the weights in the same way that we did in our work. Are there any other questions before we finish the presentation part?
So probably what this question might be whether better whether in the our group meeting, but whether you showed the two different types of the deep learning estimation, one from training with TNG 300 and another with the ASIM simulation. So both of the results has some similarity, but there's many difference, especially on the outside region. So which data do you think is more proper, and do you think which way we can test the validity of the result?
I am not sure. So, I mean, if I look at just one structure, I would say that Shapley, for example, should be more proper in the ASIM prediction, because it's supposed to be a very, very big cluster, supercluster actually. While in the TNG, it's, I don't know, it seems very small. But yeah, I don't know how we can, I mean, I guess we can try comparing to other reconstructions, but then the issue is that, for example, the Cosmicflows collaboration reconstruction, the resolution is definitely not the same. So that's an issue. And I mean, there is one thing that I would say that is not correct in both of the maps is, for example, for coma should be round, and we have like it's very elongated. We have the redshift space distortion because we place the galaxies at the redshift for the training, so we have the RSD included in the prediction. So this is definitely not correct, but we can't really do anything about that. So one thing would be try to correct this, but this is not simple. But then I really don't know how we can say that Hydra is better, like it's closer to the reality in this case, or in this case. I don't know how we can really check that.
Thank you.
Okay, we have reached the hour, so I'm gonna thank Alexandra again for that very nice talk and stop the recording.